This is the video lecture for Section 1.2 Divisibility, Part 1. We'll start with the definition of divisibility. So let a and b be integers with b not equal to 0. We say that b divides a, or b is a divisor of a, or b is a factor of a, which is denoted with the notation b and then a vertical bar a, provided that there exists an integer c such that a is equal to b times c. In symbolic form, b divides a, provided that there exists a c and z such that a is equal to bc. Okay, now keep in mind that when we say b divides a, it really means b divides into a evenly. So b is the divisor, or the factor of a. Now in the case that b does not divide a, then we write b, and then we have a vertical bar with a little tick mark through it, a. As an example, let's show that 3 divides 18, and 18 divides 18, but 4 does not divide 18. Now, according to the definition, 3 divides 18 holds, provided that there exists a c and z, such that 18 is equal to 3c. Well, this statement is true with c equals 6, so 3 divides 18. Now, 18 divides 18 holds, provided that there exists an integer c such that 18 is equal to 18c. And this is true with c equal 1, so 18 divides 18. And finally, 4 divides 18 holds, provided that there exists a c and z such that 18 is equal to 4c. Well, since there does not exist an integer c for which 18 is equal to 4c, then 4 divides 18 does not hold. Therefore, 4 does not divide into 18. Now we have a couple remarks with some simple properties of the divides relation. So first, for all integers b not equal to 0, b divides 0. And second, for all integers a, 1 divides a. So this is saying that all non-zero integers b divide into 0, and for all integers a, 1 divides into a. And these are both straightforward to prove. So to prove 1, we'll suppose b is an arbitrary non-zero integer. Then b divides 0 holds, provided that there exists a c and z such that 0 is equal to bc. And since this is true with c equals 0, then b divides 0. Second, suppose a is an arbitrary integer. Then 1 divides a holds, provided there exists a c and z such that a is equal to 1c. Now since this is true with c equal a, then 1 divides a. For another remark, we have the statement for all integers a and minus a have the same divisors. So an integer a and its negative have the same divisors. To prove this, let's suppose a is an arbitrary integer, and let's start by supposing b is an arbitrary divisor of a. We want to show that b is also a divisor of minus a. Now since b divides a, then a is equal to bc for some integer c. Then minus a is equal to b times minus c, which implies that b divides minus a. Therefore, every divisor of a is also a divisor of minus a. Now suppose b is an arbitrary divisor of minus a. We want to show that b is also a divisor of a. Now since b divides minus a, then minus a is equal to bc for some integer c. Then a is equal to b times minus c, which implies b divides a. And therefore every divisor of minus a is also a divisor of a. And combining these two results, we can conclude that a and minus a have the same divisors. For one final remark, we have first, for all non-zero integers a, absolute value of b is less than or equal to the absolute value of a for all divisors b of a. So the absolute value of the divisors is less than or equal to the absolute value of the number being divided into. And secondly, we can state that a non-zero integer has only finitely many divisors. To prove one, let's suppose that a is an arbitrary non-zero integer, and let's suppose that b is an arbitrary divisor of a. So we want to show that the absolute value of b is less than or equal to the absolute value of a. Now since b divides a, then a is equal to bc for some integer c, and taking absolute values, this implies the absolute value of a is equal to the absolute value of b times the absolute value of c. Now note that since a is non-zero, c must also be non-zero, which implies that the absolute value of c is greater than or equal to 1. So c is an integer, and the absolute value of c will be a positive integer, which, since it's non-zero, has to be greater than or equal to 1. Then, looking at this absolute value relation again, absolute value of a is equal to the absolute value of b times the absolute value of c, and since the absolute value of c is greater than or equal to 1, this will be greater than or equal to the absolute value of b as required. So this proves our first remark here. Now for 2, we'll suppose that a is an arbitrary non-zero integer, and we want to show that it has only finitely many divisors. Well, every divisor b of a must satisfy the inequality in 1 that absolute value of b is less than or equal to the absolute value of a. And this can be written in the form minus the absolute value of a is less than or equal to b is less than or equal to the absolute value of a. Now since there are only finitely many integers between minus absolute a and absolute value of a, then there are only finitely many divisors of a, and that proves 2. Now the following result will turn out to be very useful when dealing with divisibility, and the proof is one of the homework exercises. So we'll state this as a lemma. For any a, b, c in z, so for any integers a, b, and c with a not equal to 0, if a divides b and a divides c, then for any r and t in z, a has to divide the linear combination br plus ct. Next, we want to talk about the greatest common divisor. So we'll start with the definition, and we'll let a and b be integers, not both 0. Then the greatest common divisor, or GCD, of a and b is the largest integer d that divides both a and b. Therefore, d is the GCD of a and b, provided that 1, d divides a and d divides b, so this is saying that d is a common divisor of a and b, and 2, for all integer c, if c divides a and c divides b, then c is less than or equal to d. And this is saying that if c is another common divisor of a and b, then c must be less than or equal to d. So this is the greatest part. Now the greatest common divisor of a and b is usually denoted with the notation a and b enclosed in parentheses. And this is obviously a somewhat confusing notation, since 2 elements in parentheses is used to denote points in the Cartesian plane, but this is the standard notation. For an example, we want to show that the GCD of 18 and 30 is 6. So we'll look at the positive divisors of each of these integers, 18 and 30. So the positive divisors of 18 are 1, 2, 3, 6, 9, 12, and 18. The positive divisors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. So then the common divisors of both 18 and 30 are 1, 2, 3, and 6. And the greatest common divisor is obviously 6. So the greatest common divisor of 18 and 30 is equal to 6. Now the most straightforward approach to determining the GCD of 2 numbers is to just list all their divisors as in the preceding example. For large integers, however, this approach will be very inefficient. So the Euclidean algorithm, which will be presented later in this section, gives an efficient approach to finding the GCD. Next, we want to define 2 integers a and b to be relatively prime, provided their GCD is equal to 1. For an example, we can show that 45 and 28 are relatively prime. And to show this, let's look at the positive divisors of 45 and 28. So these are respectively 1, 3, 5, 9, 15, and 45, and 1, 2, 4, 7, 14, and 28. And so we see that the only common divisor is 1, so the GCD of 45 and 28 is equal to 1, and therefore 45 and 28 are relatively prime. Now in the two examples above, it turns out that we can write the GCD as a linear combination of the two integers. If we look at the GCD of 18 and 30, which was 6, that is equal to 2 times 18 plus minus 1 times 30. And the GCD of 45 and 28 was 1, and this turns out to be 5 times 45 plus minus 8 times 28. Now the next theorem shows that the GCD of any two integers can always be written as a linear combination of them, so this is not a surprise. And this property will be used frequently when working with the GCD. So this is theorem 1.2. For all integers a, b, and d, a and b not both 0, if d is equal to the GCD of a and b, then there exists not necessarily unique integers u and v such that d is equal to au plus bv. So the GCD d can be written as a linear combination of a and b with coefficients u and v. Furthermore, d is the smallest positive integer that can be written in the form au plus bv. We'll start the proof. So suppose a, b, and d are arbitrary integers, a and b not both 0. And let's suppose that d is equal to the GCD of a and b. So we want to show that there exist integers u and v such that d is equal to au plus bv. Now according to the second statement in the theorem, the greatest common divisor d will be the smallest positive integer that can be written in this form, as an integer linear combination of a and b. This provides a clue how to prove the theorem. Let's let S be the set of all positive integer linear combinations of a and b. So S will be the set of all things that look like am plus bn, where m and n are both integers, and am plus bn is strictly positive. So this is the set of all positive integer linear combinations of a and b. Now by applying the well-ordering axiom to the set S, we can show that S has a smallest element, which according to the theorem statement should be the greatest common divisor. So there will be two main parts to the proof to show this. First, we want to apply the well-ordering axiom to the set S to show that it has a smallest element. And second, we want to show that this smallest element is in fact the greatest common divisor of a and b. Now to apply the well-ordering axiom to S, we need to show that S is a non-empty subset of the set of non-negative integers. Since the elements of S have the form am plus bn, where a, b, m, and n are all integers, and where am plus bn is positive, then S is clearly a subset of the set of non-negative integers. By definition of the set S, it contains positive integers, so it will be a subset of the set of non-negative integers. Now when m equal a and n is equal to b, then the linear combination am plus bn will be equal to a times a plus b times b, or a squared plus b squared. Now since a and b are not both 0, then a squared plus b squared must be strictly positive. So one of a and b must be non-zero at least, and then the square of that will definitely be positive. Therefore, a times a plus b times b will be an element of S, which implies that S is non-empty. And then by the well-ordering axiom, since S is non-empty, S must contain a smallest element, and let's call it T. Now since T is an element of S, then it has to look like elements of S, so it's going to have the form T is equal to AU plus BV for some integers u and v. Now we want to show that T is the GCD of A and B. That is, that T is equal to D. Okay, so D in our original hypothesis was the GCD of A and B. To show this, we need to show that t satisfies the two conditions in the definition of the GCD. First, t has to be a common divisor of a and b, so t divides a and t divides b. And second, for all integer c, if c divides a and c divides b, then c is less than or equal to t. To prove the first part of 1, t divides a, we'll use a proof by contradiction. So let's suppose that t divides a is false, which means that t does not divide a. We then need to derive a contradiction. Now by the division algorithm, dividing t into a, there exists integers q and r such that a is equal to qt plus r, and 0 is less than or equal to r is strictly less than t. Now since we're supposing that t does not divide a, then the remainder r must be greater than 0. It cannot be equal to 0. Now solving for r, we obtain r is equal to a minus qt, and substituting t is equal to au plus bv, we obtain r is equal to a minus q times the quantity au plus bv. And we can rewrite this as a minus aqu minus bqv. And factoring an a out of the first two terms, this is a times the quantity 1 minus qu. And grouping the minus sign in the third term, with the minus qv, we get b times minus qv. Now, this shows that r is a linear combination of a and b. So r is equal to a times 1 minus qu plus b times minus qv. Now, since r was assumed to be positive, that tells us that r is a positive linear combination of a and b, which means that it must be an element of S. But r was less than t. That was the remainder when dividing by t, so it was less than t. And t was the smallest element of S. So this gives a contradiction. We have an element which is less than the smallest element of S, which belongs to S. And the contradiction arose from supposing that t did not divide a, and so thus t divides into a. A similar argument shows that t divides b. So this proves 1, so t is a common divisor of a and b. Next we need to prove 2. Now, before we get to that, just to mention that the method used above is a standard technique to prove one integer divides another, and will be used many times in the course. So using a proof by contradiction, we start by supposing the first integer does not divide the other. And we then apply the division algorithm, and our hypothesis implies that the remainder must be non-zero and hence positive, and we use that to derive a contradiction. Now to prove 2, we need to show for all c and z, c divides a and c divides b implies c is less than or equal to t. So this is going to prove that t is the greatest common divisor of a and b. So let's suppose that c is an arbitrary integer, and we'll suppose the hypothesis c divides a and c divides b, and we need to show the conclusion that c is less than or equal to t. Now since c divides a and c divides b, then there exist integers r and s such that a is equal to cr and b is equal to cs. Then t, which was equal to au plus bv, substituting for a and b, we obtain cr times u plus cs times v. And we can factor a c out of that. This will be c times ru plus sv. And since ru plus sv is an integer, this implies that c divides t. And by one of our remarks above, this implies that c is less than or equal to the absolute value of t. But since t is positive, then we obtain c is less than or equal to t, as required. So this proves 2, and therefore t is the greatest common divisor of a and b, and hence t is equal to d. And this completes the proof of the theorem. Now the converse of theorem 1.2 is the following. For all integers a, b, and d, a and b not both 0, if there exists integers u and v such that d is equal to au plus bv, then D is the greatest common divisor of A and B. Well, this converse turns out to be false in general. That is, it's possible that D equals a linear combination, D is equal to AU plus BV of A and B, but D is still not the GCD of A and B. However, in the case that the two integers A and B are relatively prime, so that the absolute value, the GCD of A and B is equal to 1, then the converse does hold, as stated in the following corollary. And the proof of this corollary is one of the exercises in this section. So the corollary says, for all integers A and B, not both 0, if there exist integers u and v such that AU plus BV is equal to 1, then the GCD of A and B is equal to 1. Now the following corollary, for which the proof will be omitted, gives an alternate definition of the greatest common divisor, where the second condition in the definition is replaced by the condition for all integers C. If C is a common divisor of A and B, then C divides D. So this is corollary 1.3. Let A and B be integers, not both 0, and let D be a positive integer. Then D is the greatest common divisor of A and B, if and only if D satisfies the conditions. First, D is a common divisor of A and B, so D divides A and D divides B. And secondly, for all integers C, if C divides A and C divides B, then C divides D. So this is just slightly different from the definition of the GCD. Now note that in general, A divides BC does not imply A divides B or A divides C. So if A divides a product of two integers, it doesn't necessarily divide one or the other of the two integers. For instance, 6 divides 3 times 4, which is 12, but 6 does not divide 3, and 6 does not divide 4. In this example, note that 6 shares non-trivial factors with 3 and with 4. Now, in the case that A does not share a non-trivial factor with either B or C, then A does divide the other, as stated in the next theorem. So this is theorem 1.4, which says for all integers A, B, and C, with A not equal to 0, if A divides the product BC, and A and B are relatively prime, so the GCD of A and B is 1, then A must divide C. And the proof of this will suppose A, B, and C are arbitrary integers with A not equal to 0. Suppose our hypotheses, A divides BC and the GCD of A and B is 1. We need to show that A divides C. And to show this, according to the definition, we need to show that there exists an integer k such that C is equal to AK. Now, since the GCD of A and B is 1, then theorem 1.2 implies there exists integers u and v such that AU plus BV is equal to 1. So the theorem tells us that the GCD can be written as a linear combination of A and B. Now, multiplying this equation by C, we obtain AUC plus BVC is equal to C. Now, since A divides BC, then BC is equal to R times A for some integer R. Then substituting into the R equation, we have C is equal to AUC plus BCV, and this is AUC plus RAV, and we can factor an A out. We'll have A times the quantity UC plus RV. Now, since UC plus RV will be an integer, this implies we can choose K to be UC plus RV. And since U, V, C, and R are integers, then K will be an integer. And then C is equal to AK. And this proves the existential statement, so C divides A. And this completes the proof of the theorem.